Now we look at the thermal energy transfers associated with the cycle. I haven't labeled the states 1, 2, and 3, but these are the same states that we just looked at. During the constant volume increase in pressure, corresponding to the water going up the tube again, there's a delta Q that goes into the system at constant volume, so that the amount of thermal energy that goes in is going to be NCV delta T, number of moles times the number of joules per mole Kelvin times the number of kelvins. And we can determine N, again, using the ideal gas law. If we know the pressure, volume, and temperature in the first state, which we assume we know, then we can find N very easily, just PV over RT, and we get our delta Q. Okay, now we go up to a temperature T1, which we write down explicitly is going to be P naught plus rho GH over P naught times the original temperature. Actually, I should call that T2. Let me make the change. Because this is state 1 and this is state 2. State 1 to state 2. Okay? So we got an explicit expression for our temperature here. So if we know our high temperature, we can find out what our change in volume is here. And of course then we know our temperature difference between T2 and T3, so we can get our NCP delta T. This expansion takes place at constant pressure. Pressure is not going up, it's not going down. We have this NCP delta T, that's our delta Q in this cycle. So that the thermal energy goes in here at constant volume, goes in here at constant pressure, and if we know the three temperatures, we can find the delta T here and the delta T here, and find the work that goes into the system. Now, one way or another, the system gets back to its original state, and it probably doesn't follow a path like this. Actually, it's probably going to expand and come back. But one way or another, the system does get back to its original state, and the work done, the net work done by the system in the cycle as it gets back to its original state is the area inside the curve, because the area under a pressure versus volume graph is work. And you can work out the units of that. That's not difficult. Now, the question is, how much delta Q goes out of the system? And how does the delta Q get out of the system? There are lots of ways we could get delta Q out. We could just let the system cool down, and as it cools down, the pressure will decrease and the volume will tend to at first remain the same and then to decrease. So maybe we would go down like this and then like this. So we might have almost a square region. There are other ways to let the system cool down, and what really happens depends a lot on cooling rates and other factors. What we want to do is we want to look at a couple of specific ways that the system could cool down. Okay. One way to cool the system down is to just open a valve and let all the excess pressure just escape, or just, well, we don't really let pressure escape. What we're letting, what we do when we open a valve is we let some of the gas escape, decreasing the number of moles N, which decreases the pressure. So that we're going to have a curve that looks like this. We start here at our high temperature, and we let the gas, we open a valve. Gas escapes. The pressure of the gas then very quickly goes back to atmospheric pressure. And this happens quickly. Since it happens quickly, there's no time for thermal energy to be exchanged, so no thermal energy comes out of the system here. Okay? Then the system can cool back to its original state at its own pace. Or we might just decide to blow some cool gas into the system, replacing the gas. But one way or another, when we do that, we lose the thermal energy that remains in the gas after the quick expansion. Now, in a quick expansion, we again lose, we exchange no thermal energy, but the gas expands, so it does work. And that work comes at the expense of the thermal energy of the gas. It follows that the temperature of the gas decreases, because temperature is a measure of the average kinetic energy per particle. If the thermal energy of the gas of all the particles decreases and the number of particles doesn't change, then the average kinetic energy per particle must go down, which means the temperature goes down. So when a gas expands, it tends to cool off. When it expands quickly, it's got just about no choice but to cool off, since there's no time for delta Q, no time for thermal energy to be exchanged. In this case, this curve is characterized by PV to the gamma as a constant, where gamma is the ratio of constant pressure to constant volume specific heat for that gas. Now, this is different from between diatomic and monatomic gases. We haven't yet talked about exactly what that difference is, but this is what we get. Now, PV to the gamma is constant. Gamma is something we can easily determine if we know these molar specific heats at constant pressure and constant volume. We can determine the value of this constant because we know pressure and volume at this state. It's going to stay the same all through this curve as it is at the original state. So by putting in the pressure at this state and the volume at this state, and raising the volume to gamma, where gamma is this power, multiplying by the pressure, we obtain the constant, which allows us to express pressure as constant over V to the gamma. That gives us a function that we can graph and get the actual shape of this curve. Now, this is called an adiabatic expansion. Adiabatic expansions are typically quick expansions, but the definition of adiabatic is no exchange of energy with the system.